you know, the type of science we're going to be involved with. Huh? You're on, okay. Okay, so I'll be talking about, I changed the title slightly just to emphasize what I'm doing in my research and with my group, which we call ourselves the Solar Wind Sherpas, because we carry all our equipment, the sensitive ones, on our research. So just a reminder that this is an eclipse picture from 2008, from the eclipse of 2008, and it has been processed by Miloslav Druckmiller. And this is what most of you are used to, is what we call a white light picture. But beyond this picture, there's far more information than just what this picture is giving, although it carries a lot of information. So just to remind you, fundamental bright line in the corona that was not seen on Earth, and they called it coronium. It took about 70 years to identify this line as that from iron that had been stripped of 13 electrons, and that could only happen if the medium was at 1,000,000 degrees or more. So it was, the consequences of this were far-reaching. First of all, it meant that the atmosphere of the sun was not just sun and other stars. Opened up the whole a huge scientific window, space exploration in solar physics and astronomy. Is that spectacular details of the corona that it's simple enough that you just have to take a measurement of the spectral line and the neighboring continuum, and from measurements or images, you can detect, you can tell exactly what is occurring in the corona. And this is the first time it has ever been done. It's possible. It's because these correlations, as I told you, the prominences of this material in the corona. Now, in this example, there was a prominence that. Now, what happens? You can see here that some of the material is full, some of it escape. And if it escapes, does it escape? Does it get ionized, or does it stay cool? So this is another, these are observations taken in 2013, where you can see that in the eclipse, CMEs, forming the core of CMEs that escaped, that were captured during the eclipse. And you can see from the, in different states of its evolution. So in, sorry, I don't want this. Okay. So in 2015, we had designed the spectrometer before, but it was the first time that we had very good weather observations. And we got spectra. And the idea was we have two channels. So the light is coming through here, and then there's a mirror that's reflecting it. Filters, I don't need to go through all the details, and you have two gratings. So one of the channels was centered on the iron 11 line, and the other on the iron 14. And the idea was to measure not just the intensity, but also the shape of the spectral line to see if there were motions other than just outflows, but non-thermal motions or turbulence due to waves. So the size of the spectrometer is literally, it fits in a carry-on, in a roller, small roller. Now, the other design was such that the image of the slit, so it had a slit, it could be captured because the slit was a mirror slit, so it could be captured on the image of the corona as it came through this lens. So that was very helpful in telling exactly where the slit was in the corona. So these are three examples from the different positions of the slit during the totality. And in 2.5 minutes, we started from sun center, from central meridian, and we went out to 2.5 solar radii. And instead of getting, you know, just what we had originally planned, we found that there were actually very strong Doppler shifts, and the Doppler shifts were redshifted away from the observer. And in addition to being it to 1,500 kilometers per second. So we put this information all together. So the slits were moving from central meridian all the way to the east limb. And these different little segments correspond to segments along the slit, which had material that was boundaries indicate the ones that had prominence material with them. So you can see that in these observations, there were some that was one that was going at 1,250 kilometers per second, and these two at 1,500. So the interpretation is that we caught a CME front going away from the observer, and embedded in this hot material were parcels of cool material. So clearly, I mean, these observations are providing a very, very important information, because there is at present no other instrument that can do spectroscopy in this distance range. Okay, so our plans for this coming eclipse is to have a triple channel spectrometer. We just changed slightly the design. And then we choose the band passes in each channel so that we can have, now that we know what can happen, we have cool or cold coronal plasma. We have plasma at less than 1.5 million degrees, and you have hot coronal plasma at over 1.5 to several million degrees. So this way, whatever material is in the corona, you can actually capture it, hopefully, and you can also capture Doppler shifts if they're present. So this is now, in addition, we're also going to carry out the imaging we have been doing for a long time, because now we have almost a solar cycle of images covering, well, they're not continuous, but they cover a solar cycle where you can of the temperature in the corona. So on the left is one filter here, and the camera is at the back, and this is the spectrometer. So our plan now is to have 3 major sites in the western part of the States, and the reason we didn't go all the way to the east is because I didn't have any funding from NSF to expand further. Now, in addition to these 3 major sites that will have identical instruments, imaging and spectroscopy, we have 2 secondary sites in Wyoming where we will just have imaging. So that takes me to the end of my talk, and if you have any questions.
Varsha, I'm sorry, Shadia, that's a terribly interesting work. Can you tell us something a little bit about your setup? That imaging system looks incredibly complex. How long does it take to get that set up and prepped and calibrated before you do the eclipse observation in that 2 minutes?
This was the first time we put all the cameras together on one mount. We will never do it again. Because usually what we have is we have 4 of these cameras. Okay, so for every coronal emission lines, we have to have a pair. One pair is at line center, and the other, one camera is at line center, and the other one is in the neighboring continuum, because you need to subtract the 2 to isolate the spectral line. So on one mount, we can have 4, so basically 2 spectral lines. And now the cameras, we have developed a software so that you can just run it, and you go through a sequence of exposure times. And so one mount can carry 4. And the spectrometer, obviously, is on a mount by itself. But here we put everything together, and it was a nightmare.
And a quick follow-up. So you have students involved in
Yes.
running these observations. And so how do they get distributed across these eclipse sites?
Okay, so usually I don't give a student the full responsibility of a few days, to set up. But then, you know, the alignment and the focusing and so on was done in the field prior to the totality. But during totality, he ended up having to run. He did extremely well. He obviously has nerves of steel. So, any other questions? Okay. Well, thank you very much. So, Jay is with us. Sorry. Okay. We crashed PowerPoint.
Okay.
Okay. You can start talking if you want, and then I'll.
Let's try one more time.
Yes, it
We
will
can
come up.
change to my computer if this won't work.
No, it should work, but it's just tired.
We do both things at the same time.
No, I closed mine, but don't want this one. Sorry. How come?
Ah.
It's waiting to go.
It's not ready yet. Okay. Thank you very much, Shadia. She and I agree on all the important science to be done at eclipses. In fact, Claire and I discussed DKIST in the last break, and we learned that they claim from DKIST coronagraphic capability red, and the sky background at the top of Haleakala, which has had coronagraphs in the past, should be down to about 50 millionths of the solar brightness. But as the people here know, so there still is substantial room for work at eclipses, much darker sky than we have even at the wonderful conditions of. I am going to use Michael's map and her own work. So I want to start with these few eclipses from 2012 and 2015 and 2016. 2012 in Queensland, Australia, 2015 in Svalbard, and 2016 in Indonesia, with 2013 in Gabon. And for my few minutes here, I want to concentrate on the relation of the eclipse work to the LASCO observations, and often with pasted on ultraviolet images from a variety of spacecraft that we now have. Space Agency, the Royal Observatory of Belgium, and now the GOES 16 spacecraft. And here is that only on the days of eclipses can we fill in this donut that is absent from the space observations. The helioseismic magnetic imager takes magnetic field observations. We also get magnetic field observations from the ground, from the Woodcock Solar Dynamics Observatory, have a 1,000,000 degree or 2,000,000 degree observations, a relatively cool channel of only perhaps 10 to 50,000 degrees from Solar Dynamics Observatory. We were able to use SWAP, which is run by an alumnus of my university, Dan Seaton, to see the eruption on the surface and then follow it up through the C2 coronagraph from the Naval Research Laboratory, which is on the SOHO spacecraft, which is already more than 20 years old, and then further out on the right side of the screen in the C3 coronagraph with a wider field of view, but also a wider occulting disk from that spacecraft, from LASCO on SOHO. And also I work with other people, Ron Dantowitz, Wendy Carlos, to put together some of these images to the overall shape of the corona. We've been following the shape of the corona over the solar activity cycle for longer than one cycle. And here is one of our processed images going in the donut between the silhouette of the moon and the LASCO observation, which you note is fairly round. There are streamers going out on all angles. We have the porcupine of the sun, and we've been able to publish in the Astrophysical Journal an article on each of the last several total solar eclipses, and then often with a spectroscopy, which I'm not going to discuss today, and the continent as we needed to. And here's a wide field map from Michael Zeiler showing the extent of the partial phases in addition to the totality. And you can see that even the beginning partial phase even included a little bit of New England. These are composites of dozens of individual images. This one was made by one of our colleagues from Thessaloniki in Greece, and you can see the extreme contrast to which this has been developed. You see a nice coronal mass ejection on the top. We also have spectra. You can see some of the spectral lines that Shadia talked about, in particular the fainter red line and the little brighter at that occasion, the coronal green line, which is from a higher temperature, and we've been able to see the ratio of the two change as a function of the sunspot cycle. Here is a beautiful LASCO image of this big coronal mass ejection here with our image, and an inner image from SWAP in the middle, and Miloslav Druckmuller, who everybody here knows, did make this beautiful image from our observations with two coronal mass ejections shown there. And we can put together our processed images with this beautiful LASCO image, and then we can paste on SWAP if we want to do it to get this complete version. And this image here is all smoothed out to lessen the joins. But in particular, the images that we get at the eclipse can be only a few arc seconds, whereas the LASCO at the eclipse in the overlapping region. So when we get a clear day, we can see the corona much further out. And I guess Shadia showed a related movie there. So here's the sunspot cycle. You can see that the latest cycle is only about, the solar maximum was about half. Is there a pointer here? I guess not. Was only about half the height of the preceding cycle. Thank you, Xavier. Thank you. So whether there's some longer cycle working or not, we don't know yet, and we don't know what's going to happen next. But just to show you this later cycle, and later on I'll show you today's version of this map. You can see Soho has been up the longest, and then Trace is defunct in that it was taken over by Solar Dynamics Observatory, and you can see here the Proba 2 spacecraft launched there in SDO. Anyway, in 2015, and again, I'm just giving you the highlights, especially to link with the space results. The path, as you know, went up in the Arctic, barely clipping the Faroe Islands, and I was at Longyearbyen, and you can see in Michael's calculations the extended shape of the shadow when it reached Svalbard. So here's a Proba 2 result with a nice eclipse. And then if you were on that spacecraft, you would go halfway around and you would get a second eclipse. So it'd be fun to be up in space to see these eclipses someday. And these pictures are taken every few minutes, so we were able to get a map of the sun as it rotated over the whole month. I asked for 2 weeks before and 2 weeks after, so you can see how the structures are evolving and how they came up to what you were seeing on eclipse day, and we can then map the external parts with some eclipse observations. So it's best to use these together. I've been working recently with Rand Dantowitz, who's an excellent photographer here. So you see for a while, because it's been solar maximum, there have been streamers on all levels. And now we won't have many polar streamers extending on the poles, so we'll be able to see the plumes better. Here is a later image. This is the sunspot cycle as of the time when we had the 2015 eclipse. You see, we're just past this double peak cycle. It peaked at different times in the northern and southern hemispheres. And I worked with my undergraduate student, Allison Carter, in getting these images and the space images from Dan Seaton, and Wendy Carlos did this work in putting all those images together. in Yimin and extending out in the corona, and you can do it from the east limb and the west limb and the front. And at the moment, the spacecraft are more or less on the far side of the sun. I'll show you a picture of that later. So here is a combination of our images. You can see the streamers extending out into the LASCO C2 images. And we were able to have Michael and Polly with us, and various other colleagues from various places in Svalbard, as we had earlier Michael and Polly with us in Gabon. There are these partial eclipses in which it's okay to have a few clouds during the partial eclipses. But even when we are not having a good eclipse on Earth, an eclipse in a transit is measure the quality of the instrument. So you know you have a sharp edge essentially at that time. And Proba 2 did get a good J here. And then we have these wonderful, and we were right here, and Shadia was a little further up in the path, and then it went out into the Pacific, where it passed one little atoll where a crew from the Exploratorium in San Francisco got some observations. And so here we were in Ternate with about 2 minutes and 42 seconds of eclipse, and you can see that the sunspot cycle was already declining at that time about a year ago in 2016. And the conditions were not perfect where I was. Some people got better holes. We at least could see all the phenomena through a hole in the clouds. And we could model the inner corona. We didn't get the outer corona on that occasion. Just for comparison, I wanted to show you the coronagraph. This is the K coronagraph on the Mount Mauna Loa Solar Observatory run by the High Altitude Observatory. So this is the quality of the coronagraph observations, and that's not that different from what the new DKIST will be able to see, and they could make an image, but the images are nowhere near as good as the images we get from eclipses. Here's the LASCO C2 observation with still some fairly high latitude streamers. The actual active regions aren't above 30 or 35 degrees in latitude, but like a porcupine, they go off in all directions and cover the pole. Here's the Proba 2 a partial eclipse there, and you see we just got some partial Smithsonian Center for Astrophysics, and they got quite a nice eclipse from from the Hinode XRT. We've seen some of the space maps before, Hinawari, so this real umbra going across the Earth will certainly have beautiful pictures from the spacecraft this time. The Discover shadow can be seen very well, so we certainly hope that Discover continues. And here's 13 images put together from this epic camera 4-megapixel device on the Discover satellite. I mentioned the stereo satellite, so NASA has these two satellites from different points of view. Stereo A, where A stands for actually ahead and B for behind. Stereo B, one is slightly inside, one slightly outside the Earth's orbit, so they go at slightly different speeds, so they've gotten to different distances around. There is a coronagraph on each of those, and there is an imager also with several channels on each of those. That's stereo ahead, and you can see that by the time of this eclipse a year ago, they had drifted all the way, more or less halfway around, so we're seeing the backside of the sun fairly directly. Let me just mention the last couple of eclipses, which have been annular eclipses. September 1st, 2016, in the Indian Ocean, where I was out in the island with Xavier and some other people in the Indian Ocean on the French island of La Réunion. And it's very convenient with Xavier's work to be able to plot out the local circumstances. And so then we just had an annular eclipse, which is always fun, but not like what we all hope to see on August 21st. But here is a sequence that shows the effect there, and then arranged in different styles by my former student Muzhou Liu, who's now a graduate student at the University of Colorado. And then just a little over a month ago, we had the eclipse that went across Chile and Argentina that you heard about from Mike Kentrianakis earlier. It did go into Africa a bit. Here's Michael Zeiler's beautiful map showing the extent of the partial phases. You had just seen Xavier's map before that, and it was very clear. We got beautiful images in the partial, and we saw nice Bailey's beads at the beginning and at the end from the center line, and you saw Mike's interesting images from the side. And so a few people went from the side. I'm still going to stick to the center line. I like the center line. I like the symmetry. So different people have different pleasures in seeing an annular eclipse. But this was certainly very nice in Patagonia, and it was fun to see the beads. And here's the Proba 2 a partial eclipse on that occasion. And here is a movie from Proba 2 of that eclipse. So we do have these assets in space from up till now from NASA and the European Space Agency. This Proba 2 has on it, in addition to that swap camera, this some measurements in the ultraviolet, the Lyra instrument, and here are different wavelengths in the ultraviolet and the normalized irradiance over time. And Solar Dynamics Observatory was not in a position to see the eclipse, but did follow the sun. Here's an overlay of several different colors, several different wavelengths. You can see a coronal hole coming out there at the time of the eclipse, and discover did get the shadow going across, and the Terra satellite. For an annular eclipse, it doesn't get really as dark, but here's a view from Terra. Now, the National Oceanic and Atmospheric Administration has launched the first in the latest series of GOES satellites with GOES-R, and some brilliant person figured out that even if the cameras are looking at the ground, the solar panels are looking at the sun. So for the last years, there's been a solar camera mounted alongside the solar panels, and that has been very efficient. And we hope now with the new GOES series, and it is being funded, it was announced, and it is funded at a $12 billion level. That's probably not all funded, but there are supposed to be 2 more to be launched plus a spare. And so it's a huge thing, and here's the solar camera, and it does look at these different 6 pass pans every few minutes, and here are the temperatures in a logarithmic scale, million-degree gas getting above 1 million, and then some even 10 million for part of this, or close to 10 million. And the field of view of SDO is here, and the field of view of the GOES 16 is even bigger, is a bigger field of view, so we can see a little further out. And I'm just finishing in a few minutes now, Shadia. But here's a series of images from that have been released from the GOES 16 at its different wavelengths at the end of January, and you can see how the sunspot image has really fallen off. This is posted today, April 1st, 2017, and you can see that we're really going into solar minimum, and we'll be very close to solar minimum or at solar minimum at the eclipse this summer. Here are the daily images, and you can see many days there are no sunspots on the sun. Just a few days ago, 27 March, they did release this image with these coronal holes. But so we hope that everything will be functioning. Won't be probably everything in regular order for August 21st, but most things will be in order. Here's the solar monitor from yesterday, and you can see a number of sunspots on the sun and the coronal hole, the southern atmosphere at the southern border. So there are some sunspots. Maybe we'll have some sunspots this summer. From Alex Young, I did get his treatment of the 2006 eclipse, which is last solar minimum, so I wanted to show this in particular because this is more like what we should have this time in August, and things will be much more equatorial and releasing the polar plumes to be seen better than they have been for the last few years. And Alex did some very interesting reduction with wavelet analysis here, and I don't have time to go into that further here. But we do continue to take these solar minimum observations, we hope, now and link them with the spacecraft observations. And of course, Ernie has told us where to go. And just to jump ahead a little bit, I have a crew who's been with me very often, from Slovakia, from Greece, now from Boulder, from Yale, from Boulder. MIT people will help me run some very high cadence observations of coronal loops as a test of methods of coronal heating. And we have a lot of alumni coming from Williams College, and I do have 8 new undergraduates who signed up to work with me this summer. And just in closing, for solar snacks, and we saw some examples before, some of my students here put together some solar eclipse snacks, and so we have a partial eclipse, and then we had the totality with the corona and prominences. And then we just had some H alpha out of eclipse view. And then we had solar minimum. And then we had solar maximum. They didn't exactly distribute them right. And some prominences. And a coronal messy ejection. And even an annular eclipse there. And some transit of Venus, just to boot what are chocolate chips for. So I'm grateful to my students for working on this. So that's all the time I have for today, and thank you for inviting me, and thank you, Shadia, for arranging all this meeting. Is there a question? Yes. Oh, yes. Go ahead.
Thank you.
Thank you.
So, Jay, I actually have 2 quick questions.
Whose is this?
One is, if I understand correctly, there's a total solar eclipse that will be visible from Chile in 2019.
Yes.
And
I'm
wondering
another in 2020.
Both in Chile.
In Chile and across to Argentina.
Well,
In 2019, it's actually at the end, will be low in the sky. It's coming across the Pacific. And
Okay.
then it's more centrally in the path in 2020.
Am I correct that the 2019 eclipse will be visible from some of the astronomical observatory sites, or is it out of the path of totality?
Cerro Tololo and some of the other things are visible. In fact, I wrote to the director at Cerro Tololo half a dozen years ago. I said, I bet you're surprised to know that you'll be in totality in 2019. And the answer I got back is, as a matter of fact, Jay, I've been waiting to hear from you.
Yeah, good. So I was going to ask, does this offer any particular scientific opportunities?
For reasons I do not understand, the people with 1 meter, 2 meter, 5 meter telescopes are reticent to point them at the sun.
Sure. But I'm thinking the high altitude site is that
Yeah,
this might be...
Except for the new 4 meter where they know what to do. But
I was going to say that I understand, I think that the Gemini site is considering taking proposals for use during the solar eclipse, so that's in the very early
yes.
stages.
So there is a theory, for example, of putting a polyethylene bag over a big aperture and observing the infrared. There are some possibilities. We've talked about guillotines, where you can cut a rope and put a safety in as soon as the partial phases, as soon as totality is over. We tried that with a 1 meter telescope in India, and we didn't succeed in convincing them about that. But there are some possibilities, but not as many as you might think with the big observatories. It's really the logistic support.
And it sounds like the site itself does not offer anything that you have not...
Maybe some good seeing, some high altitude, but so we're glad to have their collaboration. Customs collaboration can be very useful in getting the equipment into Chile, as we saw the Easter Island eclipse. But I would love to use one of the bigger telescopes for high resolution on the corona, and we're working on it. I can mention, similarly, we were able to use the VLA for the 2012 eclipse in radio. Now we know that we have the Owens Valley extended array with some lower resolution from the Goldstone Apple Valley array in California. We're talking with the director of the National Radio Astronomy Observatory about the VLA again. And for which, of course, we would like to have some active regions on the disk.
Okay, I think I've run out of time for other questions. Thanks.
I think we have to move on now. Thank you very much. So Fatma is our next speaker.
Thank you.
You took the microphone. Jay?
All right.
Thanks, Jay. I think I'll just clip it. Can you hear me? Am I loud enough for? Okay. 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 All right. I'm Padma Yanamandra Fisher, for people who don't know me. I'm a physicist by training. I study light scattering in various media, and by experience I've fallen into planetary science, and now I'm finishing the loop with eclipses of the moon and the sun. I want to thank Shadia and AAS for their support for allowing me to attend the meeting. My topic is polarization science of eclipses, but listening to all the talks and the fact that I have 20 minutes, it's a topic that won't probably fit into the scope of the talk, but I'll do my best to emphasize why polarization studies of the eclipses, especially solar, are very interesting. Okay, well, Lika yesterday gave a nice overview of the science of the coronal science, especially in the for the sun. And basically, I'm not going to define all these terms because we've been hearing about all of these things in the last couple of days, and I'm sure many of you are already familiar. But the sun mostly, just for a basic understanding, the sun has three components: the interior, the core, the visible surface, which is the photosphere, and then the atmosphere, which consists of the chromosphere, the transition zone, as well as the corona. Now, the corona itself can be then has three primary components depending on where the light in the corona comes from to the observer. So there's the K corona, the F corona, and the E corona, which are essentially the innermost corona, which is the K corona, due to continuum scattering by the free electrons that are present there. And that is the region that is mostly visible to us during the naturally occurring total eclipses. And this is a region that's covered mostly when you're looking at coronagraphs images, because of the stray light restrictions and all. They cover that region, and so this can only be probed by the ground, from the ground, by amateurs or by professional observers, and only during the true total solar eclipse. So here's a diagram that I borrowed from Gold and Pasokov. It essentially shows on the left side, on the vertical scale, you essentially see the density of the of the material, and it's plotted as a function of distance from the center of the sun in terms of solar radii. And what you notice is, okay, I'll use this. What you notice, this is the K corona for the corresponding to solar max and solar min, and this is the E corona that comes from the emission of material farther out, and this is the F corona due to absorption of the light, and this is basically it's variable, as is the E corona. But the K corona is strongly is scattered only by free electrons, and therefore it's strongly linearly polarized. And that's a property that makes it very interesting and also unique to be able to study the K corona specifically and during total eclipses, because this is a region between 1.1 to 2.3 solar radii that you do not really get to sample otherwise. And so from this, if the sun were a point source, this would be 100% linearly polarized light. But the sun isn't. It's an extended object.
there's a lot of structure in the corona, and therefore what we notice is because of this, complicates the geometry, therefore the polarization of the light is not 100%, but much less than that. So why is the study of this corona so important? We know that the corona is many orders of magnitude hotter than the photosphere, and the farther out you go, the higher the temperature. Therefore, what drives the coronal heating? That's the key question that still hasn't been answered very definitely. There are competing hypotheses that basically call upon magnetic field lines and or nanoflares that basically carry the energy from the photosphere into the corona and thereby generate the heat there. So that's the reason that this region of the K corona, or the inner solar corona, as we call it, is very important. As yet, there's no spacecraft that's available that's going to do this. Maybe Solar Probe will be the one to do it. The inner corona, again, like I said, is dominated by free electrons. And also, the observations basically will give us a distribution of the polarization in the two-dimensional field, and from that we can basically determine the polarization brightness. Do I have, okay. And from there we can invert it, and from modeling we can extract the local electron density, which is heterogeneous and varies according to the way the coronal structure varies, and this coronal structure we know is tied to the solar activity. So between maximum and minimum, you have different types of corona that you see structure. And so therefore, trying to get a database of how the electron density varies is important, so that you can actually see how to model it, you can determine where and how, if there are local heat sources that are being generated in the corona. So these are all pieces of evidence that help you, but they don't give a unique answer yet. So you've seen a lot of beautiful images. Everybody has their own favorite images. To me, these are some of the interesting ones, because on the ones with the red background are composite images that, like Jay explained just a while ago, it's okay, I'm sorry, I don't have a, let's see. Okay, basically the innermost image and the outermost image are from spacecraft. As Jay called this the donut, the white structure that here you see of the corona, this is from ground-based observations. And that's the only way you can fill that in right now. And similarly, this is another one. They were taken between 2006 and 2016. And the aim of this comparison is just to show you that the coronal structure does vary. And since we know that in the inner corona, we basically have linear polarized light, which can be related to the oh, thank you. We know that we can relate this to the electron distribution. It shows us that this is also varying, and that's also key to our modeling purposes. And here this pair is basically the solar maximum and solar minimum from 1980 and 1994 from the HAO archive, High Altitude Observatory archives. And this shows how the corona changes. And like Jay mentioned, that you have these streamers, and at minimum, you get mostly equatorial features, and at maximum you get all this all around almost, so it covers up any kind of polar plumes that might be there. And so that would be something to look for this eclipse. But again, it also tells you that the electron distribution and the polarization changes quite a bit from one state to the other. So here are some what I call legacy observations. The 1998 total solar eclipse center point was over Curacao, Venezuela, and High Altitude Observatory had an expedition on which POISE was a polarimeter that was on that experiment. And David Gilmore is one of our team members who was on that expedition. And these are the type of observations and the products that we expect from a polarimetric sequence. That is, you get the intensity, and also this colored image is the angle of polarization. You can see it varies because of the color used for different angles. And then here's the product of the brightness versus and the polarization. And then when you combine all these images, you essentially get the polarized brightness. multiplied by the angle of linear polarization, which is this. And so you can see that the distribution of the corona in terms of polarization, it varies around the disk. And so this is important. This is the type of set. These are the observations that are going to be important to put into models to determine the line of sight distribution of electrons and to be able to get a handle on what is the mechanism for coronal heating. So our experiment, which was is supported by the NASA ICE program that Lika has initiated, we call it the PACA PolNet. What we're doing is we're partnering with Citizen Kate experiment that you heard about today and yesterday. And what we're doing is we basically have two sites that are selected when the blue stars, I guess they slipped off the graph a little bit, but they'll be in Teutonia, Idaho, and Carbondale, Illinois, which are co-located with Kate sites because our experiment essentially builds on the heritage of Kate experiment. That is, we have standardized it to have the same telescopes as the Kate experiments, and we are co-located with them so we can compare the polarization. The only difference between the two setups is we have a polarimeter that's going to be a module that's going to be mounted on the telescope versus a Kate experiment telescope, which won't have that. And so we're in the same location with the same weather effects, the same instrumental, the same teams, that are the same training, and the data acquisition, data analysis. The initial data analysis will be the same. That is, it'll be taken. The data will be taken and sent to Matt and his team in Tucson. And so the initial processing, everything is the same. So this speeds up our learning curve. And so we only decided on 2 because if it works for 2, it can work for 3, depending on how well you train your teams. And David Gilmore, who's helped with the polarimeter design, he's going to be in Teutonia, Idaho, and I will be with Matt's student Adriana in Carbondale with Bob Bauer's teams of Kate teams. And so essentially this is these polarimeters are based on the POISE experiment, and therefore the data that we expect to get are very similar to the previous images. So that's the what are the advantages of the multi-site polarimeter network? Basically, we can get multiple images and multiple observations of the inner corona from different locations, so we extending the database. We can also get large amounts of polarimetric data and sample it across the solar cycle as you monitor different eclipses. And this also includes our bridges citizen science by students, teachers, professionals, amateurs. So you get both the science and you get the citizen science aspect here. Plus, it also feeds into the STEM program. So there's multiple auxiliary benefits of this kind of a network. But then how do you engage the public? Can you actually see polarization? And how do you give them examples of it? This is something I have thought long and hard. And this is a slide I borrowed from one of my other talks that I talk about when we're looking for studying planetary atmospheres with polarization or exoplanetary polarization. And so if you look at rainbows, glory, or halos, these are atmospheric phenomena that we see on our own Earth. And basically, these are all polarization manifestations, but the process that gives rise to polarization is very different. So you learn something different about each medium. For example, rainbows are basically light scattered by very small particles in the atmosphere. If you look at halos, those are mostly from ice particles that are suspended in the atmosphere, and they're hexagonal, not spherical, and not water. So you can differentiate between what's in the medium, and you can use these kind of information also when you have spacecraft around other planets to see if you have ice or water in the atmosphere. And this one is from Venus Express. Basically, they've used this to determine the water drop, the liquid droplets in Venus atmosphere is made of round sulfuric acid, and that's due to, by looking at these kind of phase angles, you see these are Earth, but then look at them on the different planets, and you necessarily not see all of them. So it gives us idea about the different types of planets. So these are phenomena that people have already seen before. So short of setting up a lot of demonstrations, this is something that one can basically use to explain the concept of polarization and the fact that polarization is the end product. That's what you watch and you see. But what causes the polarization tells you something about the medium through which light is being scattered. So so the question is polarization unique for eclipses? And the answer is no. What it does is it provides you a very specific window to a part of the eclipse of the solar corona that we normally cannot access right away. But you can study for the total eclipse of the moon in 2015. We observed from the 8-meter telescope in Japan, in Subaru, the Japanese telescope, and we were able to actually see before eclipse and after eclipse how the signals change. And also, you can study mineralogy of the moon, asteroids, aurora on planets, and also basically plumes on different satellites looking for optically active molecules for the habitability. And also, like Lika mentioned, you can also use this for transits of exoplanets across their host stars. So all of these are kind of tied in because, and polarization, like Sharia mentioned, she mentioned imaging and spectroscopy. Polarization is a third orthogonal remote sensing tool for any observer. So if you have these three, basically you get almost a lot of the information about your system. So in summary, we do have a two-site identical telescope camera polarimetric setups, and these are along two locations, Idaho and Carbondale. This basically is a map of the next few total eclipses in 2024 and 2045. And so this is we chose Carbondale because that's going to be the crossroads for the next one also. And so we can, so what we do today, we can improve our demonstration and measurements based on what we get from here for the 2024. And we are still developing some demonstrations. I do have some polarized film slides that at least we can cross them and show students or anybody who's interested how light basically gets attenuated between filters. And so we're going to be able to develop some more of these and hand them out where we will be. And I'm glad to share any ideas with anybody else who wants to do citizen science. But this is also can be used for studying the solar system and beyond. Thank you. Oh, do you need the microphone?
No, you answered the question.
Okay. Okay, sure. Cool.
Very interesting talk, Padma, and great contribution to the science that can be done with eclipses. My question is for your slide that showed the earthly analogies for the spherical water droplets and the hexagonal stratospheric ice crystals. You can do kind of a ray tracing exercise and understand the images that you're getting. But I wonder if you can look at the phase angle versus brightness, and can you derive a particle size from that, from the scattering medium? Do you know?
Not with just one observation, but you have to have multiple angles. And if you do, you can by looking at the phase curve, especially at backscattering. Yes. And then spherical particles will have a very sharp backscattering. And also, if you're looking at mid-phase angles, that's where you will see if any spherical effects will give you the glory, but if you don't have that, that means it's a non-spherical particle. So you can, you may not be able to derive the exact size with just one or two measurements, but you can rule out certain types of particles.
But you can identify the mechanism, me-scattering versus, yes. Okay.
Yes.
Okay, thanks very much.
Thank you. Oh, I'm supposed to give you the mic. Yes. Instead of you running after me.
Thank you.
So I'm Xavier Jubier from France, as most people I guess know. Today we are not going to speak about eclipse maps. There is a connection with the maps, but you will see later. But I don't even know if I'm going to, in fact, start the talk, because it's just coming in. There will be no great American eclipse. Unfortunately, delta T, which we use, to make the maps, just slipped by 12 hours, and now the eclipse is shifted over Europe and China. So maybe we can, all leave. So that's a good joke, but of course we have a presentation. What I'm going to explain is a new method to measure the solar radius. The measurement of the solar radius has been, going on for the past century. In fact, the value we are using to make the eclipse predictions is coming from a German that, in fact, computed this value in 1891. Okay, so long ago. We are still using this value, which I will show later is incorrect, and by quite a margin. However, during all these years, many experiments have been made. Many attempts have been done also during solar eclipses, which is one of the methods that you can use, in fact, to compute this radius. The problem is all those methods usually use filters, solar filters. So they remove, in fact, some of the information that is crucial, in fact, to make a good measurement. So the goal, in fact, is to combine multiple, to improve, in fact, the method by allowing, in fact, to view the data that is, hidden by the solar filter, for example, and to combine it, in fact, with simulations that are done by my specialized application for solar eclipses. So nowadays, we can, in fact, simulate what's going to happen years later. And by matching, in fact, pictures, videos, you can then, of course, be certain that what you're seeing is exactly, what was predicted. So I'm going to, go, fast because we don't have, much time. It's maybe better to answer, questions for the people that, do have, questions. And we can, spend, more time, maybe a bit, later on some of the slides. So I'm going to take a basic example taken last year during last year's total eclipse, over Indonesia. So those two pictures at second contact and third contact show you the last beads and the first beads. As you can see, the duration between the two pictures, it's about 2 minutes and 39 seconds. Okay, and this is, from the camera, so you can be certain that this information is correct, most likely to at least 100th of a second. Okay, but the thing is, if you use the standard solar radius, even if you use the true, lunar limb profile, you get a prediction of about 2 minutes and 40 seconds, so more, which means that the solar radius is, of course, bigger. It has to be. There is no other, solution. And it's very clear that you do have, beads. This is clearly the photosphere. There is no doubt about it, okay? You don't need to have, for example, a flash spectrum. We will see a bit later, some flash spectrums. But anyway, it is very clear that it has to be increased. So now I'm going to take a very special type of eclipse, the ones that are hybrids. So they, along the path, they can, there is a transition between annular to total, and sometimes it becomes again annular, or the reverse, total, then annular, and total again. You have different, possible combinations. In 1987, that particular one was just a broken annular over Gabon in Africa. And that picture was taken without solar filter, just because of there were some thin clouds. Yet, you can see between the simulation made with my application, it perfectly matches the picture. But this simulation is done with a bigger solar radius. If I use the standard value, it doesn't match. And the difference is huge. So there is no doubt that already something is wrong somewhere. And the only thing that we don't know with great accuracy is, in fact, the solar diameter. Now we know the moon, we know the position, of the sun, the Earth, and the moon. So the only thing that we don't know yet with great accuracy is the sun. The reason is that, of course, it's a ball of gas. It's not, a rocky, body like the moon, like the Earth. So it's more difficult also to measure. And also we have a problem with there is no unified definition, in fact, of the solar radius, because we are speaking about the photospheric solar radius. Okay, so from the photosphere, the visible, part of the sun. Okay, so we have to be. It's quite difficult, and you can, of course, have different values depending on the definition that you take. In the case of solar eclipses, you always, in fact, speak about photospheric extinction or reappearance. Okay, so the beads equal photosphere. So they are either gone or visible. I'm going to show the same eclipse, but 3 different times. Again, you can see before the maximum, after the maximum, it does match. There are a few things you cannot see it on those pictures, but because the scale is a bit too small. But there are some details on the pictures that give you a hint at what you should look at, and we will come to that later. Another example of an hybrid, again, it was in Gabon a couple of years later. So this was taken again with, my application was controlling the cameras, taking the pictures. So you have every 0.3 seconds, you have an image that was taken. So you have, the beads, and I'm going to show you the simulation, if it works. Yes. So you will see the simulation is matching perfectly the pictures. But this is with an increased solar radius. With the standard one, it doesn't work out. And you notice some small details, a bluish tint. We will come to that a bit later. So this can be done in real time. So now we are going to come to the flash spectrum, because this is going to give you the key, in fact, to a better measurement. As you can see, maybe I could use the... okay. There you see a couple of small beads. Okay. By the way, this picture was taken with a camera that was unfiltered. So all the filters, were removed. So it's more sensitive, in the infrared as well. This is why, the picture is a bit, reddish. So there you have some beads. But as you can see, there is some type of glow remaining. And the tint of the glow is bluish. You don't really see it on the picture, but it is bluish. If you look on the flash spectrum, you have the continuum, that is the main bead, and on each side you have many lines, and this is in fact what we can call the mesosphere, the low first ionization potential. This layer is between the photosphere and the chromosphere. So if you can know exactly where this layer appears on your picture, you can perfectly time the contacts. So by combining the simulation plus the pictures plus a flash spectrum, you can know exactly what's happening. I'm going to show at different times. So you see there is an evolution. And if you look here, for example, you have some photosphere with some mesosphere mixed. And you can find it again. And the same on top. So you have the main bead, some smaller ones, and the mesosphere on both sides. And you have it. And for example, you have a cut. You find a cut as well on the flash spectrum. So as you can see, the simulation is perfectly matching. Okay, there is no, photoshopping or whatever. Because, some people, of course, will ask the question, but you can do it, with the application in real time. So, I'm not cheating, it's not like, a geographic, system. I cannot, remotely control your screen. Okay, so again, there, anybody, can in fact use my application and obtain exactly the same results. Okay, so this is why also I want people to be aware of it. For example, next August, I would love, if some people, would do those, flash spectrums, because the more, we have, the better. It's quite easy to do. Of course, we need to have, some good resolution as well. But anyway, it's a fairly easy experiment to do, and the results, can of course, be absolutely fantastic. So hopefully, more people will, get into it. So this is really, the key: matching the simulation with the flash spectrum and the pictures. This can give you exactly the solar radius. So now we are going just to have a look. We take, of course, the flash spectrum, and we cut it horizontally to know exactly the wavelength that we're observing. So I have, cut the flash spectrum at different heights on the flash spectrum, of course not on the sun. And you can see that you have 3 different layers, because you have 3 different types of curves. Of course, you have always the main lines. For example, H alpha, it's that one. That one is, I think, H gamma. The blue part is the photosphere. Okay. The red is the mesosphere, the part that we are interested in fact, to measure, the sun. And the black part is the chromosphere. So if we look at it, that one, the lines that we are interested in are there. So this is the part that you have to, in fact, look for. So now I'm going to come back to the annular that Mike, Kentrinakis, showed you earlier during the day. So they were just, in fact, outside. This is the southern limit with the regular, the standard, 959.63 arcsecond solar radius. This is with 960. Okay, I know from all the previous eclipses that the solar radius is slightly lower than 960. So they were, positioned just outside of what most people, would consider, the real, path, but yet inside the true one. And of course, their results did perfectly match the simulations. And we are going to see some analysis of the pictures. So on the right, the picture taken. On the left, the simulation. There are quite a few things that you have to, look at. First, of course, the position, the shape, the intensity of the beads. By the way, this picture is taken, of course, without any solar filter. It's not something that people, should do, of course, on a regular basis, because it's dangerous. So you have to know exactly what you're doing. But it's possible to do it. Why do we do it? Just to reveal the information that we need to look at. If you use a filter, this information is hidden. There is no way you can get it back. So what we are looking for is, you see some of the chromosphere, but you see also some bluish tint. This is what we're looking for, the mesosphere, because you find it also on the simulation. So if you can match this, then you have a good measurement. And I'm going to show another one. In a way, it's even clearer because you see you have some, cuts because of the valleys and the peaks, on the moon. And you find exactly the same pattern on the picture. Same intensity, same position, same, shape. For example, this part, this is the mesosphere. It's exactly the same thing. So most people, when they look at those pictures, they would interpret the mesosphere as the photosphere. So they cannot time accurately, in fact, the contact. There is no way they can do it. So you have to, have both in parallel, and of course, a flash spectrum to be able to confirm. Of course, otherwise there is no way. I mean, you could create a simulation that does match, but without being the proper, layer of the sun. Now I'm going to give an example in 2012 of an annular taken with a solar filter. A picture taken every second. As you can see, it's not possible without the simulation to time anything. I have a much better resolution, for this image, for example. I cannot tell. At best, I can say maybe at half a second, what is the contact time? But I'm not even sure that there is a contact time. If I use the simulation, then yes, I can, exactly, time it. Otherwise, it's impossible. So if you use a solar filter, it's nearly, impossible to really, get any meaningful result. You can, of course, try to, match some beads, but there is some information that is hidden. So unless you have, a very specific pattern of beads, it's very difficult to get any meaningful information. So this is, the software that I'm using. It's free. Of course, donations are, accepted, and I would say welcomed, because it's constantly being improved. It's also the application that Michael is using, for his maps. So there is a special module. He can, generate, his gridded data points. There is also now a module, to study the flash spectrum. So it's fully automatic, and you can, calibrate and do absolutely every operations. So, for the layman, in a way, it's possible to do the whole experiment. You just have to have a camera, a grating, and more or less you can do it. Of course, the results may not be that great. You have to spend a bit more time on it and try to practice, but it's possible. And I would like people to, in fact, spend some time on it. It's quite interesting, and at least you get something that can be useful also to all the people. So it's not just taking pictures. There's much more behind. In a way, you're doing also science without even knowing that you're doing science. So that's it. So. Yeah, just one more thing. Okay, so the value I'm going to give is 960 arc second for the solar radius. It's slightly lower. I'm not going to today to give the exact value because we still have to experiment a bit more. Although I'm pretty certain that it's just slightly lower. But before giving a value, I prefer to wait a bit more. Anyway, it's very close to 960. If you use 960, you are close enough to have a good prediction right now. At least much better than if you use 959.63. Yeah.
Thank you very much.
Questions? No? Yes.
Question?
Yes, you can take the questions while I.
Okay. Yeah.
I have, Javier, this is Dave Jones. I have the microphone, so I'll ask a question.
Yeah.
What's the difference in for somebody on the ground if they're going to find a special place on the edge for the eclipse in using the current model or the current number now versus the new updated?
You can be outside. That's the issue.
So you could miss it.
Well, you don't really miss, everything, because of course you will have, many, beads, but you will never have, totality. You may also, see, a bit of the corona, very shortly, very faintly, but you miss, most of it. So, but anyway, those people usually, they take a margin, they make sure, they are, let's say, half a mile at least inside the limit that it was computed, using the regular, value. So usually their margin is big enough. But those that, venture, closer to the limit, to the edge, then of course they could be in trouble. Yeah, it's,
I'm a little confused by the fact that you're quoting a solar radius or diameter in arc seconds. Are you just assuming a distance of 1 AU? Or
yeah, we always do.
Okay, okay.
Yes. We convert it, of course, yes.
Okay,
yeah,
okay.
Yeah. Because,
And you're using the IAU number for the
absolutely, yes.
the
yes.
astronomical
the
unit?
1976, value, yes.
Okay. No, I mean for the astronomical unit, because the IAU recently adopted a numerical number of kilometers for the IAU.
Yeah, this is the value we're using, yeah.
Yeah, okay, good.
Yeah, of course, yeah.
Xavier, I have a question. Over your analysis, you did analysis over many years. Have you found a variation in that solar radius?
I can see a small variation, very small. But yeah, likely there is a small variation. It's the problem is it's very difficult to tell because, for example, the pictures, in 1987, the quality of the picture is not that great. So it's, and plus, they had, some, thin clouds. So again, those thin clouds, may hide also, something that is, behind. But I have started to look at eclipses, from 1966 because there was also a very special annular in 1966 over Greece, and there is one good, picture of it, and it does match, but I need to slightly adjust the value I have been using, for example, for last year. So there is a very small difference. When I say a small difference, it's about 1/100th of an arc second. Okay, so 0.01 arc second. But it would appear, yes, it does. I cannot say also if it's if it does depend on the solar cycle. I have no idea because there is not enough data. But I think if we apply this method for the next let's say 10 years, we may be able to give an answer.
Okay, thank you very much, Xavier. So.
So to start,
The most important.
okay, yes. To start out, though, I want to ask you a question. How wide is the mesosphere? I mean, I think that's the...
It's a couple, 100 kilometers. The fact is, I think it's slightly more than 1,000 kilometers.
Oh, wow. Okay.
Yes,
okay.
but it's again, we need to have more results, more data, and also to try to improve the resolution. Mm-hmm. But anyway, it's clearly there. There is no doubt about it. Mm-hmm. Now, of course, we have to refine the measurement.
Yes, yes. Yeah, definitely agree. That's sort of central to what I'm talking about is that there's uncertainty in these measurements of the solar radius, and it's not like this lunar grazing occultation where we had a few observers that were stationed just a few over a distance of a couple of about 300 meters or so, and they saw the star Aldebaran. You can see some partial phenomenon due to the star's angular diameter. So we're measuring the angular diameter of another star other than the sun. But with the lunar topography now, we can really target these much better. I wanted to show a solar eclipse recording from the 1998 eclipse, actually, but we can't do the AVI on this machine. So I did show it during the break a little bit, and so if we can get out of this now. Okay. Oh, you want me to click this on so yeah, here. Okay. Okay, now just get to the PowerPoint.
David, may I ask you one question while you're doing that?
Yeah.
That occultation, which I was able to see at the grazing zone in Hartford.
Uh-huh.
I
Oh,
didn't
okay.
record it, but I did see it, and we saw up to 6 events.
Uh-huh.
However, some people have said that there's been dimming, and they said it has to do with the diameter of Hartford.
Oh, Deborah, yes.
And that was doing it. But then others disagree that it's still a point source and it's not resolved.
No. It's definitely angular diameter. Yeah. Right. It's from total occultations of Aldebaran. There have been many measurements of those, and we know very accurately the angular diameter is 0.021 arc seconds or so, so 21 millarc seconds, and so that it projects on the ground a distance of about 45 meters or so. There's also a diffraction effect. If the star is a point source, you get Fresnel diffraction. You see that on a lot of lunar occultations for point sources. But that effect is over a distance of about 10 meters or so, versus 40 meters for the diameter of the star. So anyway, we want to try to determine the edge of the eclipse path with let's see, how do I advance? Just the arrow, the up arrow? Lower arrow, okay. So anyway, the eclipse this year gives us a unique opportunity to deploy much greater resources than we can usual. Of course, that's true for all of us what we're doing here. And I'm talking mainly about observations near the edges. We've done, IOTA's tried to make solar radius measurements from eclipses with sort of a checkered history, and I think Javier has hit along some of the major problems. Emphasis has been on edge observations. As I mentioned, it's the ultimate grazing occultation. How accurately can the path edges and the solar radius be measured? I think it's somewhat limited to this mesosphere question that he brought up. But with the citizen science, with many observers, this time with smartphones, we can do something more than in the past. There have been a lot of eclipses in the past that have been observed. I'll go through that. And I want to get co-located use of previous techniques that have been used. Of course, before 1950, there's been some photographic observations, but certainly in the 19th century and early 20th century, most of the observations were visual. Telescopic projected image was used by IOTA in the early years, but filtered video, telescopic video has been the dominant thing the last several years. But we want to estimate realistic accuracies. The stuff that has been done in the past is not quite right. And we want to now test color cameras and flash spectrum observations, just like Javier mentioned, I think is what's needed. So I agree with him there. But we want to reduce the older observations to see what we can get from them to the accuracies, the uncertainties that are limited. In the past, all the data we had with Watts data, and then since the Kaguya and the LRO data, we haven't had a chance to really go back and reanalyze them all. So we're no longer limited to the polar regions with the LRO data, has been mentioned. So now central timed recordings are also useful for the project, and of course that's what many of you have done. Let me go on. So we've been mainly observing near the edges of the eclipse path because of the limitations of the Watts charts was the main reason. If you observe at the edges of the path, you're always getting polar features of the moon, and the latitude libration is always near zero at an eclipse. So you get the same lunar features producing the beads. So that sort of eliminates the uncertainty in the lunar features. That's not an issue anymore, but it has been during most of the work we've done. So anyway, so we've known that the What happens at the edges, the eclipse shadow is roughly circular, and so you get this sort of sine wave drop-off. For locations close to, but just inside the path of totality, you still get some totality of the order of a half to a third or so of the duration, or a quarter at least, but you get about a 10 times enhancement of the edge phenomenon. So the Bailey's beads, the chromospheric visibility and mesospheric visibility, and shadow bands are all enhanced by greatly near the edges as opposed to the center. This just shows a lunar grazing occultation showing the observed points versus the Watts profile, and the same one now with the Kaguya profile. You can see there's a much better fit. So we've really proved that the new profiles are much better, and that was just a quick thing. And this just shows the solar radius determinations we've done with their internal consistencies, but their true errors are somewhat larger, as I'll show. But this is showing some annular and hybrid total eclipses and SDS data here. And then this is the irradiance measurements that have been made during the satellite eras. Or I think that's stuff from SOHO. So anyway, observations of eclipses, though, go way back, and we hope to get some idea with the limited accuracies from the previous ones. And Edmund Halley had this broadside sent out, distributed widely across England, encouraging everyone to watch this eclipse. And it was essentially the first citizen science experiment for a total solar eclipse. And there were three, whoops, I left out an R there. Observers reported instantaneous totality at locations near the actual limits, and so that gave us a measurement of the diameter of the eclipse. And also, he was more interested in just knowing where the eclipse shadow was. It was about 50 miles off of his prediction in those days. Let's see, the important thing is that Paul Muller investigated the published observations in the Philosophical Transactions and found descriptions of the locations where the observers were. And he visited the locations in England and talked to local historians to find out where the locations were back in 1715, and then measure them on modern maps. So that was sort of key to getting those positions. There have been some similar experiments done at other eclipses since then. One of the most noteworthy ones is the 1925 January eclipse across New York City, where gas company workers sat on the rooftops, and some of them were looking for the shadow, but the others were looking directly at the sun and told whether was the eclipse total or not. And everyone north of 96th Street said it was total, and those south of it said not. But there was some inconsistency with, some of the Boy Scouts did a similar thing and had slightly different results. But anyway, this has been done again in 1983. Dr. John Parkinson organized 25 students and set up teams of them at both the north and the south limits. And they thought that the sun's diameter was 0.34 seconds smaller than predicted, but this is now, but there were great uncertainties, because partly due to the rush training of some of the observers, as was said, or something. Anyway, at the same eclipse, Dr. Alan Fiala got the first video recordings of an eclipse near the path edges. So anyway, this just is a summary of all the eclipses that we've studied. The radius correction, showing here, but I don't have time to really discuss this. That's only the last ones that have been done, more carefully. But this shows the beads at this 1998 eclipse, just showing the sort of thing that you got, and you've seen some even better pictures that have been taken. But in 1998, we, for the first time, had at least two observers at both the north and the south limits. And so we were able to pair the observers and get different determinations. So there was a determination overall with all the observers was 0.16 for the radius correction, but you can see when you pair the different observers in different ways, you get different values. And so this is the error, just the statistical error involved, but you can see that the differences, though, are quite a bit larger. So instead of being of the order of a few hundredths of an arc second, which we were claiming at the time, the real errors were more like a quarter of an arc second. So as I said, although the former errors were small, the differences were larger. So the systematic errors and doing the different filtrations, as Javier mentioned, that was the main problem, I think, with these ones. Anyway, this Eclipse edge determination that we want to do this year, we want to mobilize people in those towns near the limits to say whether or not the eclipse happened, and if there was totality, was the last bead completely disappears or before another one, just to do it as well as they can to sort of mimic what was done in the past, so we can sort of get a gauge of this. But in addition, we want the observers to use smartphones to video record the eclipse. So we plan to work with the Mega Movie Project to use their apps and infrastructure for reporting the observations. We're just getting underway with this. We have some experience with this, which I'll mention. I just wanted to go here. Here's the locations near the path edges we've indicated. There are a number of cities that we've found that are crossed by the eclipse path with the city proper. St. Louis and Kansas City are the largest ones, of course. And we're already organizing an effort at Minden, Nebraska, which Paul Maley is setting up already, and talked to people there and visited the place. In South Carolina, we have Camden, Lugoff. We crossed that driving here, I noticed, and so that would be a possibility in this state. There are other cities that are close to the path where similar experiments could be done, but the city proper is not crossed by the path, but it's within a mile or two, and then people could easily get there. In 2014, occultation of Regulus, we tried to do this sort of thing with a cell phone app and DSLR cameras. It was completely cloudy, but at least we got a taste of doing a large-scale infrastructure project like this. This just shows the gray zone, which we define as being 300 meters outside to 700 meters inside. That's the 1 kilometer of interest where the change is the fastest for determining the path edge. And we just want to see what differences there are, see how sharp we can really say the eclipse is. I mean, this just gives us a roadmap of places to target our efforts towards. And here's a similar map of Kansas City for the southern limit. And as Javier already talked about the flash spectrum, so I don't need to say any more about that. But it's what we think is the better way to do things. So I think, when you're not doing eclipses, there are many other eclipse-like things happening. So there are transit astronomical phenomenon that you can observe more carefully. The technology now allows observers to record them much more precisely into fainter magnitudes than ever before. So there's a very small, inexpensive, yet very sensitive video camera available now. It only costs $80, which will allow you to participate in IOTA's program. You can get this, you can just get this camera and record directly to a computer with a frame grabber device, and so it gives you the chance to record occultations and to measure sizes and shapes of hundreds of asteroids, discover the duplicity of both close double stars and asteroids with satellites like this one with Antiope, which is a double asteroid. And we've had a handout there. If you haven't taken one, please do, and it gives us gives our web address and everything. And just to mention, for the reason we're going to the central part of the country, wife's brother lives in Columbia, Missouri, right at the center line pretty much, and it's at the center of the country. So rather than going for the best weather in the west, we're going to go to the center, and the reason for that is we have these other events, occultation of a 5.9 magnitude star across eastern Nebraska a week before the eclipse, and then 2 nights after the eclipse we have a graze right over St. Joseph, Missouri, with this 9th magnitude star, and the night after that there's a 10th magnitude star with the asteroid Ara over northern Missouri. So with that, please take my handouts, which gives links to all the more information about both our Eclipse project, the Eclipse Edge project, and IOTA and the general information we're doing. Thank you.
Okay, so while we're taking questions, maybe Mark can say something.
Right.
Oh, you take, it's in your
Oh,
pocket.
Yes, that's right. Okay, okay,
Yeah, why don't you hold it for a second?
okay. Any questions?
David,
Yes.
your occultation predictions for eclipses,
Yes.
do they assume a spherical sun?
Oh no,
Or-
no. We've been using the profile. We use the Watts profile, of course.
No,
for many
I'm
years,
not
but
the
now-
moon, the sun.
Oh, the sun.
The
Yeah,
sun.
oh, spherical. Yeah. We haven't tried to take into account oblateness or anything.
Is the oblateness of the sun known, and how does that compare to your errors in your measurement?
Yeah, that's. It's much smaller. It's. I think the oblateness is maybe a few hundredths or so. I think it's quite a bit smaller than the errors and the uncertainties in just getting the radius. So I think there's some controversy about the oblateness measurements, and if we have more well-timed central observations versus edge observations, then we might be able to start addressing that. So that's a good point.
Okay, thank you very much. Mark Bender, the brave.
The brave. Is that thing going through? Yes. Oh, it is? Oh, yeah, it's black. Or is it? I don't know. Yes, I'm really sleepy and tired. Not that anybody was boring, because nobody was. So I'm going to let a virtual version of myself introduce me, if it's playing. No.
Oh, it's loose.
Oh, okay. We'll start over. Thank you.
My presentation is posted. I sent a link to this solar eclipse mailing list, somewhere you can get the presentation. So
Yeah.
look at it.
That should be good. What is with this? No, I think I just turned it to black. So let's see. I'm a filmmaker, so I'll introduce myself with a previous version of myself that I filmed. My adventures as an eclipse chaser began in Cornwall, in the UK. At the time, I had no idea that eclipses were going to be so profoundly influential in my life. But as it turned out, they were. You just want to see more. It's so unexpected and so different from anything you've ever seen. The glory of the corona of the sun. I was just fascinated and obsessed, and since then I've been focusing all of my filmmaking attention and personal attention to understanding and to enjoying this beautiful phenomenon. And then I went to Africa.
Yeah.
That was so good. That was the first one, actually. Easter Island. And then I went to Spellmark, Texas. And the ring of fire was in its perfect alignment on the horizon. Indonesia. They've taken me all around the planet. They've taught me lessons that I couldn't possibly have thought they were going to teach me. And they've enlivened my life to a point where they've changed everything. My whole perception of what the world is and what it offers to us has changed and been enhanced. I want you to come with me on that adventure, because there's more. Join us on Eclipse Chasers.
Okay, I left that guy back at the hotel sleeping because he's tired now. I sent this other one. I'm here to talk about the Mega movie a little bit. And you can tell I'm enthusiastic about eclipses. And I'm a filmmaker, so one of the things I'm doing is making several films. Hold on, let me get this. Yeah, I'm making several films, a series, in fact, for a company called CuriosityStream that'll be shown in June that'll talk about this eclipse. And while I'm doing that, I'm also working with the Mega movie. So the Mega movie is mega. The concept was that we would get millions of people with their smartphones to photograph the eclipse. And initially, I thought it was a really stupid idea because I just thought, mobile phones, man, eclipses are going to look like little tiny. They're going to be like 5 pixels. So I proposed that we use very professional cameras, being a camera person, and have identical systems and film it really properly, which somebody else is doing, Citizen Kate, which is excellent because I asked a lot of people and no one would give me all the money. So that was that. But as time progressed, I started to get into the concept of the Mega movie in that all these different people along the path, if you had millions of people providing this information, that you might lack quality, but you'd get it replaced by the huge amount of quantity. So I started getting into it. And my first concept was that we should put a little lens on the smartphones. So that's what that is. That's a little 20 times lens clipped onto the front of an iPhone. It's in my pocket, in fact. And I decided I better go to Ternate, Indonesia, and see what that looked like filming an eclipse. So I went to Ternate and climbed that volcano with Terry Cuttle. And 6 hours ascent almost killed me. 5 hours descent, even worse. He marched up and down it like a mountain goat. He went up the next day as well. I couldn't walk down the steps of my hotel. Just saying, my days of mountain climbing are getting short. It was a great day. So when we got there, it was part of a location scout. Now, the difference between that eclipse, which was what, like a year ago or so, you can see that it goes over a bunch of islands. And that's kind of what eclipses have been like for a long time, for all of us who chase them. But the one in America is different because we have this massive population. This thing is going over. We have so many people available to like take this photographic information. And so back to this. Decided that we would test out some concepts. We put a camera system on this little island south of Tidore, which is south of Ternate, called Mare. I'll cut to that in a minute. And then we went to another, that's that one there, you can see. And then we flew, what, 77 kilometers or so to the east and stayed on Xavier's Island and had another camera system set up there. Those were our 2 professional cameras. You can see that there's a little iPhone kind of rig here. That's that lens that was on that first camera. And so we filmed both eclipses. That's me on the little island. I slept next to that Russian who snored all night in a Quonset hut. Eclipse chasing, not exactly glamorous. I won't even say. Okay, so from Mare, the viewing was better. And this was a frame from the professional camera, which was pretty good. And this was shooting raw video, so it's not still images. And this was a frame from the very cloudy Plun. Is it Plun? Is that how you say that? That'll do. But still, this thing cut right through the clouds. It was pretty remarkable. We got some pretty good images. And we were able to like overlap the observations so that we took this 2.5-minute eclipse and made it into a 5-minute observation that was continuous across the whole thing, which was just a pattern to do across America to capture 90 minutes of an eclipse. So that was all right. Now I took, with the little mobile phone at the same island through that massive cloud, this is with the 20 times lens. And I thought it was pretty good for an iPhone with a tiny little clip-on lens. I showed it to Dr. Paskov, and he thought it was rubbish. And I was like, okay, yeah, fair enough. So then I decided, well, I better get a bigger lens. And I got this lens, which is a 50 times lens, which I think is really disgusting looking. It just kind of freaks me out. And also, it's like twice as big as the 20 times lens, which makes it a little bit more uncomfortable to deal with. But it's basically just screwed on to a really cheap mobile phone, smartphone, Android running phone that is running our Megamovie phone app. So we then decide, oh, that's the difference between the 300 mil lens on a professional camera and a 20 times lens on an iPhone. Substantial. But if you got like 1,000 of one and 100,000 of the other from all these different locations, it could be very interesting. So that's the little setup that I took to where did I just go? Argentina, like last month. I've been making this film nonstop for the last 3 weeks since Argentina, and I'm like about to pass out. So it better be worth it. So we took that down to Argentina, and actually we took 6 of them. I took 2 colleagues, and we had 2 phones each, and one of them had the little lens on it, and the other one just is the normal, just a phone. So I was calling that the wide field, and you can just set that down and point it up at the sun and push kind of go on the Megamovie app. That image there, that's what you get when you blow up an image of a sun just from a smartphone lens. You can see that you wouldn't really get many Bailey's beads or anything because there's like, they'd cover about like 5 pixels. But still, photometrically, this could be an interesting object if you had 100 million of these all across the path. That's with the 50 times lens, which would be a better image. So we thought we could get something going on. So this is what we ended up with in Argentina, which was an annular eclipse, an image like this. And we located the 6 phones, 2 of them on the northern border, or edge of the eclipse, 2 in the center line and 2 on the south, about 25 kilometers either side of Facundo. And you can see there was a couple of problems. The app knew the time and location accurately, and it knew how to automatically take the pictures, which meant that you could watch your eclipse and your phone would be taking pictures for you. Sort of like a tiny version of Xavier's app, but even simpler. I'll get back to that in a second. What I kind of totally screwed up was that my images were incredibly badly underexposed, which means that if I'd taken the solar filter off, I'd probably have some cool data for you around the edges. Because, well, I just would have. It would have been awesome. Because these literally, when we looked at these, were black. And so we had to really bump up the gain to kind of get this image to come out. But we're pretty happy that it came out because it showed us that we had got the accurate location and the accurate timing, which maybe sounds simple, but you got to see if you can write the program and see if it works. Yes, so the time, it knew what to do, and it did it. So that's pretty cool. And this was sort of the result. Oh, hold on. Wait a minute. I just messed my result. Let's try that again. Right. Okay, that's the north and the south side, and you can see it's going to loop. You can see that the edge of this, now because it's so underexposed, we're actually missing the beads across the little edge here. But if I made my exposure better or took the filters off, we'd have a really nice little set of beads on both sides. The center camera, and this is what's fascinating to me, we tried to make this thing incredibly foolproof so that basically you just put the phone down, push go, watch your eclipse, your phone does all the work. Well, I didn't explain to my colleague on the center line how to do it. I didn't walk him through it. I gave him the camera and the lens and said, go film it. And he couldn't figure out how to do it. So even the simplest thing that I thought was like absolutely apparent kind of foiled this guy who's an experienced eclipse photographer. And so it just goes to show you when you're communicating to people, you have to be accurate and you have to make sure that what you think is simple works, because it didn't work. So I don't have the bit that would have been the beads on this side and that side, which would have covered the entire eclipse. We would have had the entire edge of the moon imaged. So these are pretty useful, I think. And if we have 100,000 of these all over this eclipse path, I think it would go a long way to working with what Xavier is trying to do to measure these parameters. So that's it. That's my whole presentation. I'm going to keep it short because I'm tired. Thank you.
Karen, did you want to say something?
That was a little joke for the end.
So are there any questions for Mark? No? We start. So Karen is the last one.
Excellent.
And I'm not going to do my PowerPoint stuff. After our meeting out there, I've got something else that'll work better.
Okay.
But I need to still hook it up to show.
Here, you need this.
I won't keep you long.
That's fine. Keep it short. Here you go. And you just stick it. I clip that under here.
Oh, I'll just hold it.
Well, you can put this on the table if you want, and then just put this on your dress or somewhere close by. Thank you, Mark.
Oh, thank you.
Well, where did it go? Oh. Okay. It's already up here. Okay. I'm Karen Roark, and I work at NASA Ames, and I'm not a scientist. I'm an education professional development specialist, and I can help with lesson plans. I can help with all that. I'm a certified national board teacher, and I'm Teacher Hall of Fame and all that. So I'm an expert at that, but I'm not an expert at your job as a scientist. But I try to get other teachers to have the love of science and start getting it out to students as low as kindergarten level. And I think it's so important because I think that we lose their attention after about 4th grade because we start having to do paper and pencil tasks. And the Eclipse is no paper and pencil task, it's action. And if kids get into action, they will have the love of science the rest of their lives. And who knows, they might be on Mars living one day if we can instill that even in the low rural schools. I was from rural Georgia, as you can tell by my accent. And I have students now at Georgia Tech and all other schools, George Washington University, Georgetown, and it's because I had an interest in them, I think, and took them to space camp, took them to all the National Geographic things, working with Dr. Bauer, the Jason projects, and even bringing in specialist scientists on we were a NASA Explorer School, and I brought him in on webinars, and that's what I want to ask for you. There's 10 of me in all the other NASA centers, and last year alone, I know this doesn't sound like a lot, but we reached person face-to-face or over webinars 34,209 educators. So just think if we could get those educators to do the Eclipse and they could get their specialists at their schools, how many educators would actually be teaching the Eclipse? And so what we need your help for, when we go into schools and stuff, it's not doing. I guess I can just do. We talk about the sun, you know, we talk to teachers and give them all the concepts that you've given us today. But one thing I wanted to share with you is, you know, the sun is a star. And a lot of students don't even know that. And stars are all different temperatures. And I think even when you go to the school settings, if you relate it to fairy tales, even when you relate the 3 bears, the temperature of the bowls, this fairy tale is written wrong. So if you have your students to do experiments to find out the different temperatures of the bowls, well, the same with the stars. You can sort of relate to them, and they know what's too hot, too cold, and just right. And then you can go into all sorts of things with this. See, because we have hotter stars, and we have sun-like stars, and we have cooler stars. And there's several different YouTube videos, and I'm not going to bore you with those, but some of them are fun and cartoons of the solar eclipse. And then I don't want us to lose the wonder. Even 3, 4, and 5-year-olds, you take them out to the sun, they're worried about the shadow. You know, they're looking and playing with the shadows and stuff. And so we can even get the young preschoolers involved. And there's a lot of preschool systems that don't have any science in their curriculum. So always keep the wonder alive. But what I really want you to help me with, well, sorry about that. Now it's gone. There's my PowerPoint, but it's not, there it is. Okay. So we'll go to. Okay, this is our website. If you can, the NASA EPDC website, and teachers can already get a badge if they want to on the Eclipse. They can earn 5 professional development hours, and it was developed by some people at, I think, NASA Goddard that actually got this one going. But they can go online, and they can register for webinars. We have about 50 webinars every 2 months. And the teachers can download the PowerPoint. They can use this activity in their classroom. And that's what I would love for people in this room to sign up for. You could use some of the PowerPoints you've actually done in these 2 days. And what we do, we just give you the website. We provide a webinar room. We send out the announcements with all 10 centers, and all these 34,000 educators are already on the email list. Plus, it's on the NASA website. And it advertises your webinar and what your subject matter is. And then they have, like if you tell me 3 weeks ahead of time, then we can advertise it for 3 weeks. Or if it's 6 weeks ahead of time, the more advertising time you have, the more people you'll have to register for your webinar. And it only, I hook you up to that website, and you go in and I make you a host, or one of the other 10 people like me make you a host, and then you have the whole hour to talk to the teachers. And then they have a chat box where they can, you can either let them write their questions in, or you can open up the microphone and you can actually talk to them. And it's like you're talking to them face to face. And then any knowledge that you can give teachers, because nowadays the system still hasn't changed. You can be a science teacher in grades K through 8 with very little science knowledge. And that's really scary because we have all these misconceptions, and they're going to continue until the school system and universities change their way. And some have changed, but there's still some that haven't. And it's still a low need on a lot of school systems, because they just want to hire teachers in there that can teach reading and math. And, you know, they don't look at their science credentials a lot of times. And so that's something that we need professional scientists to actually help with. So I would love for anyone in here that would like to do a webinar to get with us, because we need your scientific knowledge. And we have a summer program at all 10 centers, and we actually bring in 50 teachers that will be teaching the next year as their first year teachers. And this summer, we are obligated from NASA to spend 1 day teaching Eclipse activities. So if you would like to webinar and, you know, talk to these teachers, that's also a great thing. We can do activities and we can do all this, but you've got the knowledge, and it helps to hear from a subject matter expert, I think, a lot of times in these settings. So we're going to be touching like 500 teachers in June, July, and August. And then we'll also be going around and we're doing globe activities and we're doing eclipse activities in our different states. And so each one of us is sort of thin, but you know, the webinar helps, because a lot of we are finding out that we're going into the libraries some and museums some, and there's a lot more teachers that will come if you have it someplace where they can actually come and see something afterwards like a museum. They'll come for the workshop if they can tour the museum for free to give them some kind of added bonus. So that's one thing I would love for you to do. Not sure why it's not. You can see my screen is just, but, and this just is well, it's not showing. If it shows on my computer, it won't show up there. So, but that's mainly any questions. You can just take my card, and I would love to have 66 people were here. I would love to have 66 webinars, and I'm sure Kelly at Goddard would love it too, and she'll help me get you all scheduled and get you all on. So thank you so much for sharing your information with teachers, and if you need any of this stuff for younger kids and stuff, I'll be happy to share.
Any questions for Karen? Okay, so then I have the
Thank you. Was that short enough?
Yes, perfect. Okay. Okay, so we come to the end of the 2 full days. Thank you all for fascinating contributions. And before we leave, I'd like to specially thank Mike Andrianakis and Xavier Joubier. Sorry, I blanked out.
Lindsay.
Lindsay and Caitlin. Caitlin, I don't know where she's left, yeah? And Karen Teramura remotely, who have done a fantastic job in getting everything recorded and on YouTube. So we will have all those posted. So for those of you who split into the 2 groups for education and transportation, if you could keep me in the loop, or Angela, I mean, keep us both in the loop as to whether you got something or some notes, so that we can pursue that, because it's a very important activity that we can't afford to lose. Okay, any other announcements from anyone?
Yeah, we should thank Shadia too.
Oh, thank you. Thank you. I told Michael he was back.